Continuing our discussion on the concepts of probability, we said that when there is a single event happening and we wanted to calculate the probability of that event, then we simply count the number of favorable outcomes and we divide that with the total number of outcomes, and that gives us our desired probability. Okay. Now let us extend that discussion a little further and we discuss about the concept of compound probability. So compound probability, it becomes a subject of discussion when you have two or more events happening at the same time or in sequence, right? That is when we wanted to calculate the probability of event 1 and event 2, okay? This is where we use the concepts of compound probability. The good news is that we still utilize the same fundamentals, that it is still a ratio of your favorable outcomes to the total number of outcomes. But the challenge this thing, the compounding, brings to us is that how do you calculate the total space of all the outcomes and how do you calculate the space of your desired outcomes, right? That is exactly what we are going to learn today. And the key point we want to take home after today's discussion, that is also our learning objective, is we want to discuss about the methods to calculate compound probability, and we also want to discuss how to differentiate the independent versus dependent events. So let's go talk about that with the help of few examples. So in our very first and simple example, what we want to discuss is how to calculate the probability of getting two heads by flipping two unbiased coins. The first thing I want to do is I want to establish what is my experiment in this example. The experiment is the last part in this statement, which is flipping two unbiased coins, okay? So let me make a little diagram here. Let's say this is my coin 1 and then you have your coin 2, correct? Well, if you think about this, the coin 1, when you flip it, it will result in one of these outcomes. Either you will get a head or a tail. Likewise, you will get either a head or a tail of the result out of flipping coin 2, right? At this moment, I'm going to ask you one question. Does coin 1 know what is the result of coin 2 flipping going to be? And based on that result, do you think coin 1 is going to change its outcome? Well, definitely not, because these are two different objects. They are totally independent of each other. What coin 1 is going to do has no impact on the outcome of coin 2, correct? That is why we say that these are two completely independent events, and that is how you decide whether the outcome of one event is going to impact the outcome of the second event or not, okay? So at this time, I'll design a very small matrix here. This is simply to calculate your total space of all the outcomes that can happen as a result of this experiment. So let's say you flip a coin 1 and you get a head from there, or you get a tail, and then let me also put a head and a tail there. At this stage, I'm going to list down after a comma what will be the outcome from the flipping of coin 2. Well, if coin 1 results in a head and coin 2 results in a head, then that's my first combination. If coin 1 results in a tail and coin 2 results in a head, then that is going to be my second outcome. If coin 1 results in a head but coin 2 results in a tail, then that is my third outcome. If coin 1 results in a tail and coin 2 results in a tail, then that's my fourth outcome, right? So this is the space of all possible combination of outcomes from these two events. So in this case, I am interested in calculating the probability of head and head in this case. So how many ways this can happen? Well, I see that there is only one such combination out of 4 possible combinations. So then I will say that this is 1 out of 4 combinations. So this is your desired probability. So you saw that it became very easy to get this desired probability because you had all of your possible outcomes listed here using this matrix kind of structure that we had. And this was possible only by identifying what is your experiment, and it became possible by identifying that if there are two events, coin 1 flipping and coin 2 flipping, and if they are independent to each other or not. Alright, so let's go take a look at our second example. So take a look at this example. Alan has 3 handkerchiefs in a box. One is green and other 2 are yellow. If he draws a handkerchief, replaces it and shakes the box and draws from the box again, what is the probability that the both handkerchiefs are drawn are the green ones? Okay. Now here are some keywords that are going to be very useful in identifying how to solve this problem. So replacing the handkerchief after your first selection, that is the key part here. And the box contains one green and two yellow handkerchiefs. Okay, so let's draw a little flow diagram to best understand this problem. Okay, so there is my box. It contains one green and it contains two yellow handkerchiefs. Then you go for your first draw, right? Let's say this is my draw 1. And then whatever you selected, you put it back into the box, right? Then your box contains again one green and two yellow. And then you go for your second draw. What we want to calculate is what is the probability that I selected a green and I selected a green in both cases, in both of these selections. And I want to calculate this required probability of green and green in first and second selection. Okay. So at this moment, I will ask you this draw 1 that you have here and this draw 2 that you have here, even though they are sequential in nature, they cannot happen at the same time. I'll ask you this, do they seem independent events to you or do they seem dependent events to you? I will say these are two independent events because whatever your box was in original condition, it gets back to its original condition after your first selection and then you go for your second selection. So whatever you had selected in your draw 1, it has no impact on the outcome of the second draw because the box is back in its original condition. That is why I wanted to draw this diagram so that you can visualize a little bit that what really happens when you have problems like this. So let's draw a tree diagram to solve this problem. Okay, here is my box. Then my first selection is happening, right? And then there are two possible outcomes. Either I get a green or a yellow outcome. So the possibility of getting a green handkerchief is 1/3 because there is only one green and then there are three outcomes in total that could happen. That is the space of all outcomes in this experiment in the first draw, right? And the probability of getting a yellow handkerchief in the first draw is 2/3. That is my first selection. Now, if the first selection happened to be green, and then I put it back into the box and then I go for my second selection, then I will have either a green again or a yellow again. Likewise, in the second selection, if the first selection happened to be a yellow but I put it back into the box, then the outcome still could be either a green or a yellow in the second draw after the first draw, right? So these are all the possible outcomes that could happen in the first draw and in the second draw, right? The probability of having a green in the second draw is still the same as the first draw because you have a box that is back in its original condition. So these are my probabilities and I will put them here as well. Now our desired event is this, probability of green and green. And this will be our first route, right? This route that we see here, okay? So that will give you your required probability by simply multiplying all the probabilities along this path, which is 1/3 times 1/3 and it's 1/9, right? And this is precisely the benefit of a tree diagram, that you can obtain your required probabilities fairly quickly once you have identified all the branches of that selection process, okay? And this is very useful when you have a sequential process, something like this. Now let me twist this problem a little bit. Let me identify what is the probability of having a yellow and yellow. In the first selection we obtain a yellow and in the second selection we also obtain a yellow. What is that probability? So given the fact that I have this tree diagram and a yellow could happen in this path and in this path, I'm going to simply multiply all the probabilities that are along this path. Or in other words, you can simply multiply the probability of those events, those independent events, and obtain your desired results. Okay, so this was our purpose of showing you a method of tree diagram. This can be quite useful when you have events something like this, that they are sequential in nature. This is good for independent events and this is also good for the events if they are dependent on each other, especially useful when they are dependent on each other. All right, so that is the fundamental and the concept of compound probability.